Hello and welcome to this presentation here on how sound zones can be designed using techniques from speech enhancement, or more specifically optimal filtering methods from speech enhancement. This work here was presented at the Asilomar conference a couple of weeks ago, and it's a joint work between me, Taewoong, Jesper Jensen and Græsbøll Christensen, and we all from the audio analysis lab at Aalborg University in Denmark. So as you can see from the title, we're going to talk about both sound zones and speech enhancement here. And you don't have to be an expert in both of these fields in order to understand this presentation. In fact, the contribution we have made in this work here is to actually realize that we can take a very powerful technique from speech enhancement called variable span linear filtering and use that directly for designing sound zones. And this is essentially what I'm going to go through in this presentation here. Okay, but let's start now with first describing what a sound zone is if you're not familiar with this concept. So I have a very simple use case here where we have two persons, so for example you and your friend, and you want to hear a movie with the English speech, and your friend wants to hear the movie with the Danish speech. And in order to do that, we should create two zones or sound zones. So here we have one zone where we would like the English speech to be, and here we have another zone where we would like the Danish speech to be. And the way that we design these zones is that we can control a big loudspeaker array up here so that we get these two zones. And first of all, you might ask, so is it really necessary to do any control? Well, I have a very simple example here of what it sounds like in the English zones if we don't do anything.
Hvad siger du egentlig, fordi han er dovendyr, så kan han ikke være hurtig? Jeg troede, at alle isotroper skulle være lige, hvad de vil.
Yeah, and I guess you can hear that this is quite annoying. So we have to do something to solve this problem. So sound zones are not only useful in this particular application here, but also, for example, in the automotive application, where you can imagine that the people in the car, they don't want to listen to the same content, but they still want to be able to talk together, so using headphones is not an option. Also, a third application would be a festival where you have multiple concerts going on simultaneously, plus you typically also will have a residential area next to the festival area, and you want the sound to be as silent as possible in this residential area. So these are a few applications of sound zones. So this talk here will first go into speech enhancement and specifically talk about speech enhancement using optimal filtering. And once we have been through that, we will see how designing sound zones is essentially similar to doing speech enhancement. And then I have a few experimental results I want to show, and then finally I'll summarize this presentation. But let's start now by talking about speech enhancement. So in speech enhancement we have, or the problem that I'm going to consider here is perhaps the simplest case in speech enhancement, so single channel. And we have an observation y here, and then we assume that that's a sum over the clean speech, which we're interested in, and then some noise. And we wish to extract S here from Y, and we should do it so that we increase the speech intelligibility and the speech quality in S or Y, because otherwise it's not worth the effort to start extracting S if we cannot improve these two metrics. And it actually turns out not to be that easy, and therefore people have worked on this problem for many years. So the typical way you would do it is, or the way you do it in optimal filtering at least, is that you take your inputs, your observation. So here y is a vector now where we have stacked m consecutive observations. And then we filter that through a filter with coefficients in this filter vector h. And then the output of this filter, which I've denoted here as s hat, that's the estimate of the speech. If you now insert the expression for our observation, then we get what we have over here. So we have two terms. One term is the clean speech filtered through the filter, and another term is the noise filtered through the filter. And of course, what we want is that we want, so for the first term we want the speech to pass undistorted, and for the second term we want the filter to remove all the noise. And although this is possible in a few special cases, in general these two requirements, they are conflicting. So if we try to remove a lot of noise, we will typically also distort the signal, and vice versa. If we try to let the signal pass undistorted, we will typically also not be able to remove a lot of the noise. So many of the different optimal filtering techniques are a compromise between the speech distortion and the noise suppression. And I've listed a few down here. So the most famous one is of course the Wiener filter, which is a certain trade-off between the speech distortion and the noise suppression. So a few years ago, this variable span linear filtering framework was proposed, and what you can actually show is that many of the existing and well-known optimal filtering methods are special cases of this framework. And I'm now going into describing exactly what is this variable span linear filtering framework, and show that, for example, the Wiener filter and the max SNR filter here are special cases of this framework. So the first thing we have to do is that we need to define what we actually mean by speech distortion and noise suppression. And these are defined here in 3 and 4. So we simply define the speech distortion as the mean squared error between the clean speech and our estimate of the speech. And if you then evaluate this expectation here, you get this quadratic term you had over here. So Rs, the matrix here, is the covariance matrix, and Rs, the vector here, that's the correlation vector. And this last term here, that's only the energy that does not depend on h, so it's not that important here. We do the same thing for the noise suppression, so we specify first what we want, that's a 0, and then this is what we actually get when we filter our signal. And then we again get a quadratic term here with Re being the covariance matrix of the noise. Yes. So what we can then do is that we can formulate a combined objective function by just adding these two, but we apply a weight here, mu, so we can control how important is the noise suppression relative to the speech distortion. So if we increase mu, we essentially say that noise suppression is more important than speech distortion, and vice versa. If we decrease mu, we say that speech distortion is more important than the noise suppression. Yes. But that's not all we do in the variable span linear framework. We want even more control of this trade-off between the speech distortion and the noise suppression. And the way we do that is that we essentially make a low-rank approximation to the clean speech covariance matrix. And to understand how this works, we have to use this joint diagonalization. And it's fairly simple if you are familiar with an eigenvalue decomposition. So you compute the inverse of the noise covariance matrix times the clean speech covariance matrix. And then you take the eigenvalue decomposition of that. That will give you lambda here, which is a diagonal matrix containing all the eigenvalues. And it will give you B here, which is an invertible matrix containing the eigenvectors as column vectors. And we sort the eigenvalues in lambda according to their magnitude. They are all non-negative, so we just take the biggest one in the upper left hand corner and then sort them in descending order. It turns out that if you apply the eigenvectors as we have done here and here to Rs and Re, then they will both be diagonalized, and we will get here the eigenvalues when we apply B to Rs, and we will get just the identity matrix when we apply B to Re. And therefore, these eigenvalues and eigenvectors are sometimes also referred to as the generalized eigenvalues and eigenvectors. Okay, so what can we use this for? Well, B here, that was an invertible matrix, and that means that for any filter vector H here, we can just make a linear combination of the eigenvectors where the weights are in A here. So using this representation of H, we simply plug that into our definitions of the speech distortion and the noise suppression. And that's what we have done here. And we get what we have in equation 8 and equation 9. And what you can see here in equation 8, for example, is that we get A transpose lambda and A transpose lambda here. And that means that if some of the elements in lambda are 0, then the corresponding elements in A will not correspond to the speech distortion, but all elements down here correspond to the noise suppression. So we can simply make or only use the elements in A that corresponds to elements in lambda that are non-zero. Or we can enforce a particular rank for, so this is the number of non-zero eigenvalues in lambda is the rank of Rs, so we can just force the smallest eigenvalues in lambda to 0, for example, effectively making a low rank approximation of our clean speech covariance matrix. And in that way we increase the distortion a little, but we also are able to decrease the noise suppression. So in that way, by making a low rank approximation to Rs, we can trade off speech distortion for noise suppression. Yeah. So this is essentially what we have described here in 10. We make a low rank approximation here to our filter vector. We insert that in our objective. This is what we have here. And then we optimize this objective with respect to A instead of H. And then we get the solution we have here in equation 11. Yeah. So the interesting thing here is that we can vary mu and we can vary V here. And we get a number of different solutions by selecting them in different ways. And here is a simple illustration. So on the x-axis I have V, and on the y-axis here I have mu. So you can see, for example, if we select V equal to M and mu equal to 1, then we get what is the Wiener filter. And if we still keep mu equal to 1 but decrease V, then we get what we call the variable span Wiener filter. Out here, when we have V equal to 1, and for any mu, then we get what is known as the maximum SNR filter. We can also get the MVDR filter out here, that is again for V equal to M and then mu equal to 0, and so on. So the entire shaded area you see here, that's the space we can cover with this variable span linear filter. And yeah, we have a number of the well-known special cases, or well-known optimal filtering methods here, special cases. All right, so this was what I wanted to say about speech enhancement. So now I'm going to move on to sound zones and specifically describe how we can use the variable span linear filter to design sound zones. So the first thing we're going to look at is a mathematical description of the sound zone problem. So if you first think back to the initial example I had with the English and Danish speech. So imagine that we have two zones here. In this zones we have English, and here we have Danish. So that means that we would like in this zone here only to hear the English speech, and in this zone to only hear the Danish speech. The way you do that is that you first say, for example, let's look at this zone here, which we then call the bright zone. And here we want to hear the English speech. So that means that we have a desired signal, dm of n, which is the English speech. M here is the microphone index. In the other zone, we simply say that the desired signal is 0, and that's called the dark zone. And then we here for the input signal also put the English speech. Then what we do is we design these control filters here so that we will hear the English speech here and hear nothing here. Once we have designed that, we look at the other case. So now we look at this zone here as being the bright zone, and in this zone we would like to hear the Danish speech, and then this one here will then be the dark zone, and here we want to hear nothing. So, and we set the input signal here to be the Danish speech. Then we design again the control filters for this case, and then we get over here the Danish speech and here silence. And once we have these two solutions, we simply add them together, and then we get a zone here with Danish speech and a zone here with English speech. Alright, so in order to solve this problem here with two bright zones, we have to look, or we simply have to solve the case of a bright zone and a dark zone. So in the rest of this talk here, I'll only look at this situation where we have one bright zone and one dark zone. Okay, so I've talked already about this desired signal here, dm of n. So you can also describe the reproduced sound in each zone. So let's take microphone position or control point position. So these are the ones that are illustrated here. So this is a control point or a microphone. That will simply be a sum over the L loudspeakers. Over the L loudspeakers, and for every loudspeaker we compute the convolution between the input signal, the room impulse response, and then the control filter. And I've written this just as an inner product here, Q transpose times xm of n, and Q here, that's our unknown filter vector, so that's essentially a stacked version of all these filters, and xm here, that's a stacked version of the individual contributions from every loudspeaker to that particular control point, if we didn't apply any control, so if we didn't have these control filters here. So therefore we refer to xm here as the uncontrolled source signal. But of course reverberation is included here in this. Alright. So in the right zone, we measure the distance between our desired sound and the reproduced sound in the two norm, and we sum over all the microphones in that zone, and then we record the difference here over a number of samples. And then this is just a normalization, what we have out here. In the dark zone, we do the same thing. So here, what we want is 0, and we then compute the difference, and then sum over all the microphones in the dark zone and over the relevant time indices. And here again, we have a normalization. So if we do that, oh, sorry, I was a bit too quick there. What we can now do is that we can define a spatial covariance matrix in every zone. So for example, if we set C equals to B, we get the spatial covariance matrix in the bright zone. And that's simply a question of computing this outer product here over all the microphones in that zone and over all the time samples. And again, we have this normalization. And the same for the spatial correlation vector. We compute this, the cross correlation between our uncontrolled input and our desired signal. If we do that and plug that back into our signal distortion and residual error, these were defined here. So this is what we call the signal distortion, here the residual error. Then you can see that we get a quadratic term here for the signal distortion and a quadratic equation here for the residual error. And if you look at this, it's quite easy to see that this is actually the same as what we had in speech enhancement, where up here we had the speech distortion and down here we had the noise suppression. Yeah, and this is what I have in this table here, so you can see that we have the same form. Now we have Q instead of H, but otherwise it's exactly the same form, and that means that we can also design sound zones using the variable span linear framework. So one big problem in speech enhancement is that these statistics here, they are unknown, and they're quite difficult to estimate because we don't have access to the signals, because we're trying to estimate them. If we had access to them, there was no reason to start estimating them, right? But for sound zones, we know these. We have directly access to our desired signal and to our uncontrolled signal, so we can compute these. So that's really a nice thing. So for speech enhancement, this was called noise suppression. For sound zones, it means sort of the leakage to the dark zone. So this is how you should think about noise in the sound zone application. Yeah, and just to make a distinction between variable span linear filtering for sound zones and for speech enhancement, we have called this framework for sound zone for VAST. Yeah, and that's because sometimes variable span linear filtering is also referred to as variable span trade-off filtering, and yeah, you can abbreviate that in this way here. Yes, and as in speech enhancement, we also have a lot of interesting special cases when we apply this VAST framework to designing sound zones. So I guess the two most well-known methods in designing sound zones is pressure matching and acoustic contrast control, and these are special cases of this framework here. Another well-known method is the ACCPM method, which is we get that by varying mu out here and using all eigenvectors in our generalized eigenvalue decomposition. Yeah, and we also get something that resembles a Wiener filter. So PM is actually the Wiener filter of sound zones. Yeah. All right, so now I'm going to go through a few experimental results. So the first one is really just to illustrate that we trade off acoustic contrast for signal distortion. So on the x-axis here I have the number of eigenvectors V that we use, and on the left y-axis I have the acoustic contrast, and on the right y-axis I have the error. So it could, and that measures either the distortion or the residual error in the dark zone. Yeah. So you can see here that as we increase the number of eigenvectors, we also decrease the acoustic contrast. But you can also see that the speech distortion in the bright zone, that also goes down as we increase the number of eigenvectors. And here we have the residual error that goes up as we increase the number of eigenvectors. So right now ACC will be out here and PM will be out here. But by using this VAST framework, we can select a solution here or whatever. So we can really trade off now the noise suppression for the signal distortion, or the acoustic contrast for the signal distortion. Okay, so now let's return to our initial example where we want to see this movie with English and Danish And now I'm playing back first the uncontrolled one, then the ACC solution, then the PM solution, and then the bass solution in succession. And hopefully you'll be able to hear the difference.
Siger du, at fordi han er dovendyr, så kan han ikke være hurtig? Jeg troede, at alle i Zootopia skulle være lige, hvad de vil.
Are you saying that because it's a sloth he can't be fast? I thought in Zootopia anyone could be anything.
Are you saying that because it's a sloth he can't be fast? I thought in Zootopia anyone could be anything. Are you saying that because it's a sloth he can't be fast? I thought in Zootopia anyone could be anything.
Yeah, hopefully you are able to hear the difference. You might wonder about why did ACC sound so strange. And the reason is that ACC, there you will just maximize the contrast. And what it does is that it just looks for the frequency where this contrast can be maximized. And then it will only try to reproduce that frequency in the bright zone. And that's why you get this really big distortion of the signal. Yeah, so here is the setup that we used for this demo here. So we had 8 loudspeakers, 2 zones were each sampled with 16 microphones. And we also have a MATLAB demo where you can press at arbitrary points in this 2D map here and hear exactly how it sounds. So if you want to hear how it sounds not in a control point or between the 2 zones or close to a loudspeaker, you can do that. Yes, and that brings us to the summary. So what we have really shown here is that we can design sound zones using techniques from speech enhancement. So the idea in speech enhancement or optimal filtering is that you take your noisy speech vector and filter that through a filter which you have designed in order to trade off speech distortion for noise suppression, and then here you get an estimate of your speech. For sound zones you have something similar. You have a number of uncontrolled pressures, and here the index is the microphone index. Then you pass these through a filter bank, here denoted as a vector Q, and then out you get a number of reproduced vectors here that again will be a trade-off between the distortion in the bright zone and the residual error suppression in the dark zone. Yeah. And the main difference between these two cases here is that for sound zones you know the statistics, and that makes it much easier to produce a good solution than in speech enhancement where the statistics is unknown. One disadvantage of applying this framework to the sound zones application is that the dimensions of the covariance matrices are much larger than in speech enhancement. So the computational complexity will also be higher. But we haven't started to look into fast methods yet, but we have some ideas for how that can be done, but that's future work. Alright, so that brings us to the end of this presentation. There will be a paper out about this going into much more detail with many of the things, and that should be out in December or January. So if you're interested in this, I would really recommend that you look that you try and find it. It has the same title as the presentation here. Thank you.